minutes, and he's going to talk on discrete Ally type models.
Yeah. Okay, thanks a lot for the introduction, and thanks a lot for the invitation to give a talk at this workshop. So my talk will have two features common with other talks before in this workshop. The first one will be that I will be speaking about discrete Laplace, or more precisely Schrödinger operators on combinatorial graphs. The second one will be that I will be interested in the spectral distribution of these operators. Now, in earlier talks it was oftentimes so that geometry provided some interesting features to the models. In my case it will be different. It will be randomness which provides kind of some seasoning, and this means that the spectral distribution now gets a different meaning. I will be actually interested in the ensemble averaged spectral distribution of these operators, and one of the important questions in this theory is then whether this averaging over the ensemble of operators produces a function which is smoother than the spectral distribution of a single operator, which you would naturally expect. Now, recently there has been some interest in models where the dependence on the randomness is non-monotone. This means you have some random variable entering your model, and the model can depend monotonously or non-monotonously on this random variable. And the question is whether non-monotonicity still gives you enough averaging of your spectral distribution function. Okay, so this is what I wanted to talk about, but when I came here I realized that this talk is a little bit too specialized, so I changed it a little bit, and I will now, in the first part of the talk, try to explain why one is at all interested in regularity properties of the spectral distribution function when you study random Schrödinger operators from solid-state physics. And then in the second part I want to discuss how you get these results, and I want to compare the monotone and the non-monotone case. Okay, so let's start with some basics. I want to introduce some Schrödinger operators. From solid-state physics. And in the first part of the talk I will actually not distinguish between the discrete situation. This means operators on the discrete lattice ZD and the continuum situation where you have operators on RD, because for the motivation this difference doesn't matter. And now the important situation you want to understand first is the case of pure crystals, which you would model by a Schrödinger operator given by the kinetic energy plus a potential energy, where the potential energy is, so this is an operator, say, on RD, and you assume for the moment that the potential is ZD periodic. So you have a nice ordered structure, the periodicity, which describes your crystal. Now, if you have a periodic potential, this means that your operator is commuting with a large group of translations, with a large group of unitaries, which allows you to do a partial Fourier transform and partially diagonalize your operator, which leads to the so-called direct integral decomposition. So, which means you have a unitary operator U such that when you conjugate your Schrödinger operator H, you obtain an operator on an auxiliary Hilbert space, which is a direct integral. So a direct integral is something like a direct sum, but your index is varying continuously. And the integrand is an operator which acts on a smaller space. So h theta is actually equal to the original operator h restricted to a unit cell with theta quasi-periodic boundary conditions. Okay, so this means for each theta you obtain a self-adjoint operator, and it is lower bounded, has discrete spectrum. So the spectrum you can enumerate in the following way. And it turns out that the dependence of these eigenvalues of this operator on theta is very nice. So T maps into these eigenvalues En of theta, and this map is Lipschitz continuous and non-constant. Okay, and why is this important? Well, this allows you to conclude that you have band structure for the spectrum. So the spectrum of your operator looks like this. You have bands, and you have purely absolutely continuous spectrum. Okay. So now we want to move away from this very nice periodic situation, and we want to switch on some randomness. And this means that you have some crystal with impurities. So how do you model this? You still have a Schrödinger operator given by the kinetic energy plus a potential, but now the potential looks differently. You may still have a periodic part, but then you have also a random part. So here omega is some element of a probability space, and it kind of introduces the randomness. And for this V omega, you assume that it has some kind of stochastic translation invariance. I will not be precise at this moment, but later when I introduce some specific models, you will see this translation invariance in action. And sometimes you introduce here some coupling constants lambda, which is the strength of the disorder. Okay, so now when you switch on the disorder for lambda positive, something will change with the spectrum. You will obtain here at the boundaries intervals where you have pure point spectrum almost surely. Okay, so pure point almost surely, and it will be dense. And actually the spectrum will not only be pure point, but it will be actually pure point, meaning that you have no continuous component in these intervals. Okay? Of course, you lose the control over certain sets of measure 0 because you're in a random situation, so this is quite natural. And the conjecture is that in the middle of the bands, you will still keep some absolutely continuous spectrum. But this is only conjecture. Okay, so this is one of the reasons why one is interested in studying absolutely continuous spectrum for random operators on trees, because this corresponds to the limit of infinitely high dimension. Now, if one increases lambda, these intervals will grow, and it's a quite intricate question to control how large the size of the intervals with pure point spectrum is as you increase lambda. And here already an important difference to the discrete case arises. So for discrete random operators, you have the following situation, that the entire spectrum is localized for lambda large. Okay, so this means for discrete models, you have much better control of the localization for large disorder. Okay, the analogous question would be in the continuum model, if you fix an energy, then you can ask, is the lambda sufficiently high such that all the spectrum below this energy will be localized for lambda high? But as far as I know, there are no results in this direction. Okay, so maybe I should say something about like spectral and dynamical relation for these models. So if you have a vector corresponding to the spectral subspace corresponding to pure point spectrum, this means that as you let it evolve according to the time evolution governed to this operator, it will stay all the time localized in space, and it will not travel off to infinity as a scattering state. Now, if you have some some initial state which corresponds to the spectral subspace of a C spectrum, then it will travel off to infinity as you let time evolve. But there's also a different notion of localization related to generalized eigenfunctions. These eigenfunctions are actually, these eigenfunctions from the pure point spectrum are actually exponentially localized. So this means they decay very fast, and you have specific localization centers. Now, if you take an energy from the absolutely continuous spectrum, you still have generalized eigenfunctions for almost all values, but these functions are not in L2, they are not localized, but they are extended states. Okay? So this is another way how to distinguish these two spectral regimes. Good. Okay. Now, we have seen that in the case of pure crystals, you can gain a good understanding of the spectrum by considering a finite volume operator, namely the operator on the periodicity cell. Well, actually you have to consider a whole family, but if you understand it well, you know something about the operator on the whole space. So the idea is to ask, is it possible to understand the spectrum of the disordered operator on the whole space by studying some auxiliary operators on finite volumes? Okay, so this leads to a question of finite volume localization criteria. Okay, and indeed there exist certain criteria which allow you to conclude that you have pure point spectrum for your operator as soon as you have proven them. And the proof of this finite localization criteria works this way, that you consider a finite scale, and then you do an induction procedure over increasing scales. And as you are able to control the behavior of the spectrum and of the resolvent of your operator along the increasing scales, you know something about the operator on the infinite space. Okay, so I will try to give you some kind of vague clue about this, this procedure. So this is formulated in terms of, on the one hand, the statistical properties of eigenvalues, of restricted operators h omega lambda, which is equal to your h omega restricted to some box lambda. So lambda is some cube minus L to L to the power d. And this might be discrete or continuous. If it's continuous, you still have to impose some boundary conditions to make the whole thing self-adjoint. And the second thing is the statistical properties of the resolvent, or the Green's function. So this means you take your random operator, you localize it to a cube, you take some energy, and you take the kernel at the point xy, and here with the energy you will usually assume that you have a non-vanishing imaginary part in order to be sure that this resolvent exists, but later you want to take boundary values where z becomes real, and you want to understand how these functions are decaying as x and y are sufficiently far apart. Okay, so the off-diagonal decay is of interest. Okay, so I mentioned that you want to understand what is the relation of these properties as you pass from one scale to another. So let me draw a picture. Imagine that you have a large scale which is divided into boxes of a smaller scale, and I will just draw 9 boxes, but typically you should think that the large box is much, much larger than the small box, but then it's hard to draw things. Now, imagine that you know for all boxes, for all the small boxes, so the small boxes will have length little l, the large box will have length capital L. Okay, so for all the small boxes, assume that you know something of this type. So you have exponential decay with weight gamma. Gamma is some positive number for all points x and y inside of a box. So for instance, you might have, say, x here, and so let me draw it just right for a moment here, x prime and x prime here, and you know as you move from here to here how your Green's function is decaying. Now you ask yourself, what happens if I choose a point y which is inside of the big box but in some other one of the small boxes, and you are interested in the properties of the Green's function now on the larger box x, y, z. Okay? And the idea is that you use some kind of geometric resolvent inequality so that you can factorize these Green's function into Green's functions corresponding to smaller cubes, and then you hope that you will be able to pick up like factors of this type, okay, if the distances are approximately equal to L. So you pick up 3 times the exponent L, which gives you then the exponent e to the minus gamma capital L, and of course you will get some constants in front of it from some kind of error terms. Okay? So if you can implement this procedure, this will allow you to show that your Green's function is exponentially decaying on larger and larger cubes, and actually in this case for the study of random Schrödinger operators, it is so that the localization, the exponential decay of the Green's function allows you to include exponential decay of generalized eigenfunctions, and this way localization. Now there's a problem with this procedure, namely you will know such properties only with a probability strictly smaller than 1. Okay, this is something which will sometimes hold and sometimes not. Now, if I want to implement this procedure, I have to know that this inequality holds for all small boxes. Now, if for each box there's a small probability that this condition is violated, I pick up a lot of these violation probabilities, and in the end, I will know that this inequality holds for all small boxes simultaneously, only with a very small probability. So I will lose my game. This means I have to implement this procedure this way that I can allow certain boxes which are bad in this sense that this condition is violated. Okay. So what do you want to do? So you want to ensure that if things go wrong, they do not go wrong too badly. And for this you use a control of resonances. Okay. So what is control of resonances? I mean, you see that here I'm choosing a specific energy, and the question is whether I can have bad boxes, a lot of them, bad small boxes, a lot of them inside of the big box, which happen for the same energy zeta or the real part of it, right? If I have bad boxes, but they occur actually for different energies, then everything will be fine and I will be basically able to implement this procedure. So what I want to know is I want to estimate the probability that the spectrum of some operator H1 and the spectrum of an operator H2 are close to each other. Okay, and here for instance this could be my operator H1 and this could be my operator H2. Okay, and now I assume that they are stochastically independent, they are a little bit separated from each other, so I will make this assumption here, and this can be certainly estimated in the following way. I take the sum over lambda j from the spectrum of the first operator, and then I take the probability that I have a distance from lambda j to the spectrum of the second operator, which is smaller than epsilon. And here I will have to correct things a little bit, but let me just first draw a picture what I'm doing. So I have certain eigenvalues, lambda 1 and lambda 2, of the first operator. I don't know where they are, but basically I ask what is the probability that the second operator gets an eigenvalue which is inside of the small interval. Okay. Okay, so what's wrong with this formulation? Well, I mean, these eigenvalues are random as well. So I cannot just pull them out of the probability, but I can use that these two objects are independent. So this means that my probability measure factorizes, and here I have a fixed value and only the randomness of 2 of the second operator. So here I will write a 2, and here I will write the expectation value with respect to the randomness of the first operator. Okay, so this is using independence. And now we are interested whether we can bound this quantity here. So from now on, I switch to the discrete model only. Okay. Okay, so if one wishes to control this, one is interested whether the following bound holds. This is a Wigner estimate. And it's the question, the following question: is there some alpha from the interval 0 to 1 and some beta between 1 and infinity, such that you have for all energies on the real line, for all positive epsilons and for all cubes lambda, the following bound, that the probability that the distance between E and the spectrum of omega lambda is bounded by epsilon is smaller or equal than some constant times epsilon to the power alpha and the cube to the power beta. So what does it mean? So the question is, how large is the probability that given an energy E, I will find an eigenvalue which is in an epsilon neighborhood of this energy? Okay, so this is certainly some kind of statement about the smoothness or the regularity of the distribution of eigenvalues, right? Later you should think about think of sending epsilon to 0, and then you are asking how fast will this thing disappear. And if you have epsilon equal to 1, you will have some kind of Lipschitz continuity. If you have if you have alpha equal to 1, you will have some kind of Lipschitz continuity. If it's smaller, you will have some Hölder continuity. And it's quite clear that you will have some kind of volume dependence, because the larger lambda is, the larger is your matrix, the more eigenvalues you have, and so on. So the question is maybe what beta you will be able to obtain here, and the best beta would be beta equals to 1. Okay, and if you have this, then you can bound this term x there. So if you are in this position that you can find a Wigner estimate, then you can bound this by lambda times CV epsilon to the power alpha lambda to the power beta. So what did I do? I just plug in here this estimate from the Wigner estimate, and then I have to sum over the number of eigenvalues. But since I have a discrete matrix on the volume on a cube, I know that the dimension is equal to this cube, and this gives me the maximal, just the total number of eigenvalues here. Well, this is nice because I see that for epsilon small, this will become small. Okay, so this tells me that the probability of resonances is small. Well, now you can complain and say epsilon might be small, but the cube lambda will be big, because I'm interested in big cubes. So I have here some competition between a factor which is large and a factor which is small, but it is sufficient to choose epsilon exponentially small in the size of the cube, roughly. Okay, e to the minus size of the cube 1 over, say, 2d, because I have to pass from the volume to the diameter. And why is this so? Well, if you know something about the theory of resonances, you know that exponentially small splitting in eigenvalues ensures you that eigenfunctions will behave quite differently and that you can distinguish them geometrically. Okay? Otherwise, this argument would break down. Okay. Well, so this is now the part where I try to explain why you're at all interested in regularity properties and continuity properties of the spectral distribution. And now I move on to state under which conditions these results are known. So I already mentioned the name of Wegner, and indeed there is some result of Wegner proven in 1981 for the Anderson model. It was an argument based on physical intuition, but you can implement it rigorously, and it tells you the following statement for the Anderson model. So on ZD. So let me explain what the Anderson model is. So you have a sequence of IID random variables on your probability space taking real values, and assume that they have a density, a rho, which is compactly supported and bounded. So compactly supported means that these random variables take only values in a finite interval. And then you define your operator h omega in the following way. It is a discrete Laplacian plus a potential of this type. Okay, so this is a complicated way to write it. If you apply it to a function, it acts in the following way. Okay, so basically you have a 3-diagonal matrix in one dimension. On the diagonal you have a random potential, and then you have the kinetic energy. Okay, and certainly this operator has some nice stochastic translation invariance properties, because I assumed that the random variables are identically distributed and independent. So in this situation, the Wegner estimate holds with the optimal exponent. So alpha equals beta equals 1. Okay, so you get Lipschitz continuity in the energy, and you get proportionality to the volume. This is nice because if lambda is 1 here, you can divide this by the volume, and you can actually prove that the density of states is locally bounded. Okay. Okay, now I move on to the situation where you generalize the model, and where you consider an operator where you get non-monotonous dependence on the random variables. Okay, so now you consider the Wegner estimate for the discrete Alloy type model. So what's this? You have an operator very similar as the one which you saw there. So h omega looks like this. You have the kinetic energy, you have a random potential part, and the difference is now that your potential, which you saw there as delta k, looks more general. So this is the single side potential. And this is, say, a function of compact support. Now, and it could look, for example, like this, okay, where this is 0. And now you see, if you have a potential u which takes on positive and negative values, this means that your discrete Schrödinger operator depends non-monotonously on this random variable. Because if you increase it, there will be certain regions in space where you increase your potential, and there will be other regions in space where you decrease it. And this means that your eigenvalues are not moving in the same direction. Okay, and now if we assume a little bit more regularity in the Q's, namely that rho is of bounded variation and compactly supported, so you need some kind of weak differentiability condition, so a little bit more regularity for the rho's, then you still have a Wigner estimate which is slightly weaker, well, not slightly weaker, with alpha equals to 1 and beta not equal to 1 but bounded above by the number of points in the support of u, and that's a result from last year. So u is a function like this, so it has finite support, so the number of points in the support is a finite number, and this is the upper bound for the exponent which you get here for the volume dependence. Okay. This is not enough to conclude anything about the density of states, but it's fine enough to control everything what you need for this framework of proving the existence of localized states. Good. These models have been studied before in the continuum more intensively than in the discrete setting, and that's actually harder to prove them, and they are not so global results. There has been previous works by Frederick Klopp, by Peter Hislop and Frederick Klopp, by myself, and also joint work with Vadim Kostrikin. And in the discrete setting, it's kind of, you get a very nice and closed picture for these Wigner estimates, but as I said, the analysis is also simpler. Okay, in the remaining time, I would like to give you some kind of hints and motivations. What is the difference between averaging techniques for the case where you have a potential with fixed sign and a potential with changing sign? Well, I mean, this potential looks like this. So in particular, it has always non-negative values. So this is where you have here monotonicity. Okay, so something about averaging techniques. So we first consider a very simple example, maybe a trivial example. So let A be a symmetric n by n matrix. And you want to estimate now the Lebesgue measure of those t's on the real line such that the resolvent has large values. Okay, so this is the same as estimating the Lebesgue measure of those t's such that the spectrum of this matrix is close to 0. Okay, and this can be estimated easily by the sum over j equals to 1 till n. This is the dimension of the matrix you're considering, times the measure of those t's such that the jth eigenvalue is in absolute value smaller than epsilon. Because if you have spectrum close to 0, one of the eigenvalues has to be close to 0. And this is easily estimated by 2 epsilon times n. Why? Well, you can draw such a picture. Here's the spectrum of A. And then this is t, and if you have here some eigenvalues, they will behave like this as you switch on t. So if you're interested how much time they spend in this epsilon corridor around 0, so this is plus epsilon minus epsilon, you just see that it's 2 times epsilon. Now you can slightly generalize this, and you can say, I will not consider as the perturbation the identity matrix, but I will have some positive definite matrix B. And then I can add every time I have see a T, a B. So what will change? Now the eigenvalues will of course not be linear functions, but they will still be monotone functions. They will behave somehow like this. Okay. Moreover, you know that this little b which I have here will be the lower bound for the gradient of these functions. And this means, like, you are driving through a tunnel, you know that the tunnel is 2 miles long, you know what your minimal speed is during all the drive, then you can calculate how long it takes at most till you kind of leave the tunnel, and so you get this estimate. Okay? So we see it's not important that this perturbation matrix is the identity, it's important that it has fixed sign. Now, what happens if you allow for matrices which have changing sign? Well, I mean, if B has plus minus eigenvalues, then you have your corridor, and your eigenvalues can do anything in there. I mean, finally, eventually they will get out, but you have no control how long it will take. Okay. Nevertheless, it's sometimes possible to control this, and I will write a simple lemma, which is just a technical step in a paper, in a joint paper with Alex Elgart and Martin Tautenhahn. So, and it will tell you that still something can be done, and it's a determinant averaging lemma. So consider A and B complex n by n matrices, not even necessarily symmetric, and B should be invertible. Okay, and assume that you have some nice density, which is in L1 and L infinity, and you have an S which is strictly smaller than 1. Then you can take the determinant of A plus TB to the power S over n inverted, and you average over this density T, and this is bounded by 1 over the determinant of B to the power S over n inverse times L1 norm of rho to the power 1 minus S and L infinity norm of rho to the power S times some constant which depends only on C. So what's the relation to what we saw before? Well, if you the determinant is the product of the eigenvalue. So this means if an eigenvalue passes through 0, your determinant here becomes 0, so this term is singular. So the possibility to integrate this to a certain power gives you some control on how much time the eigenvalues spend in the neighborhood of 0. Okay. Well, here's an application, how this can be applied in the setting which we are considering. So the application would be that B is equal to U. U is the single side potential, and it is allowed to change sign, but B is not allowed to be singular, so this means that I have to restrict my operator to a smaller subspace, namely to the support of U. So A is your Schrödinger operator restricted to support of U. Well, because on the support of U, U is non-singular. I mean, this is precisely chosen this way. So this gives you some technical problems because you at the beginning start on L2 of Z, so you have a huge space, and now you can control determinants only on finite dimensional spaces. But nevertheless, you can get, for instance, this result. So in dimension equals to 1, and if the support of u is conveniently chosen to be 1 to n minus 1, so it has length n, and you have the imaginary part of z is not equal to 0. This is what you need for regularization. Then if you take h omega minus z to the power minus 1, x to x plus n minus 1, z to the power s divided by n, rho qx dqx is bounded by a constant which depends only on u and r. Okay, so what do? I take the resolvent at an imaginary energy, so this is well defined. Then I take very special matrix elements, namely those matrix elements which correspond, which have a distance n between them, or well, n minus 1. So this is a special choice. And then if I average with respect to a density function of this type, I can control using this statement, this property, and this can be used to implement proof of localization of the existence of pure point spectrum using the fractional moment method, which is one other alternative of proof to the one which I presented before. A restriction of this thing is that you have to assume that the dimension is to 1. In the high dimensional case, you can prove something for special classes of single side potentials. Yes, but there's a certain limit to this method, and on the last blackboard, I want to write down an alternative estimate, which is very useful, which is quite powerful and general, but somewhat weaker, and which has been used by other people recently. So powerful and general, but weaker tool. It's Cartan's lemma, and you can use it in the multidimensional space situation. So you have in n-dimensional complex space a multidisk with radius 2e, taking values in the complex plane, which is holomorphic. And you assume the supremum is bounded by 1, and that at 0 the value is positive or non-negative of f. Then you have the following control over the set of the range where f takes on small values. Okay, so this is my parameter space. This is total volume, so I normalize it. So this is a fraction where I'm small, and this can be bounded by a constant times the dimension to 3/2 times e to the minus s over log 1 over epsilon. Okay, so if you have a holomorphic function like a determinant, and actually you can also apply it to matrices, then this gives you a control where certain values are small, but it's harder to implement in this situation, and you need a separate multiscalar analysis to make use of this. And this has been implemented by Bourgain and Schlag and Goldstein and Krüger for related models. Thanks a lot.